In the last lecture, we have talked about buckling of perfect column, whereby we define the critical buckling load and what is actually meant by structural instability and why buckling is a problem of structural instability. Now, in the previous case, what happened was that the column was perfect without any asymmetry and the axial compressive load was, or the buckling load was applied perfectly aligned to the centroidal axis of the column. Okay, so there was no eccentricity of the load applied, that is, the load was not off from the centroidal axis, as well as there was no geometric as well as material imperfection in the column. You might be able to appreciate that such a condition is not possible in practice. So in practice, there is always some amount of imperfection in the column. Okay, however perfectly one develops it, there would be some geometric and material imperfection, as well as the load is also not perfectly aligned with the centroidal axis. Okay, however hard we try, there would be some eccentricity of the load applied to the column, the axial compressive load. Now, in this condition, the situation, the behavior of the column entirely changes. So, you have seen that in a perfect column, according to Euler-Buckling theory, the column will not buckle, okay, or not deform. I shouldn't say buckle, it will not deform until the load reaches a certain value, which is P critical. So at P equals to P critical, if some perturbation is given, it could buckle. However, it still remains in neutral stability. That is, when the perturbation is removed, the column regains its original shape. But when P becomes greater than P critical, it goes into unstable equilibrium. That is, the deformation keep on increasing and it finally leads to failure. So let me just summarize what we have discussed. So perfect column, according to Euler theory, okay, will deform only when P is equal to P critical. However, this is the problem of neutral equilibrium. That is, when the perturbation is removed, it goes back to the original undeformed shape. Right? And when P is greater than P critical, when P is greater than P critical, then it goes into unstable equilibrium, leading to failure. Okay? Leading to large deformation and thereby failure. And thereby failure. Okay. However, when we go for imperfect column, when there is imperfection, column or load with eccentricity. Okay, then the column will deform at any non-zero p. Okay, so please try to understand. Okay, so in the previous case it was a perfect column, and we there, even if you give perturbation to the column, unless p is going to be equal to p critical, there is no deformation. Only at p equals to p critical it is at neutral equilibrium, and when p is greater than p critical it goes into unstable equilibrium. And this whole idea was utilized to find out critical buckling load. Okay, right, where p critical was pi square ei by L square. P critical 1, the first buckling load for a pin column. Okay, so this was the case. Now let us now see this part. I mean, what is going to happen if we have an imperfect column and we apply an axial compressive load P. As I have said, it will start deforming as soon as a P is applied to the column with some imperfection. Okay, so what we are going to do today is going to analyze a pin column with some initial imperfection. So let me clear the canvas. So effect of initial imperfection. Okay, so suppose we have a pin column. Okay, so this is for pin column. Okay, so let us consider of length L. Okay, so this is the Z axis, this is Y axis, and this is the X axis. So we are going to apply two axial compressive load P and P. So there is an initial imperfection so which is we call as V0, which is a function of Z. So this is my initial imperfection or initial deformation. Why to call it imperfection? Let us call it initial deformation. Okay, and let us assume because of this applied load, this is going to further deform into Vz. So Vz is the deformation after the load is applied. Okay, so now if Vz is the deformation after the load is applied, so let us write down the moment balance equation. So if we write down the moment balance equation, so it is going to be EI which can be written as, right, because V minus V0 is the deformation due to the load, is happening due to applied load. Okay, so I can write this as EI sorry, I missed this is going to be minus, okay, so that is going to be EI d2V0 Vj square. So this can actually be written as when nu square is P by EI. Okay, so let me call this as equation 1. Okay, so as let us now assume that assuming V0z, that is the initial deformation, in terms of a sine series as n equals to 1 to infinity, an, which is a constant, into sine n pi z by L. Okay, so let me call this as expression 2. So, what, see, there is no constraint on what Vz should be. So Vz could be anything, right? But even it could be any arbitrary function. And you understand that any arbitrary function can be very well represented by a sine series. And therefore, this assumption is perfectly valid. Okay, whatever be V0z, whatever be the initial deformation, I can always express in terms of a sine series. Now what I do is that I substitute equation 2 now. So if I do so, I'm going to get d2v by dz square plus mu square v is going to be n square pi square by L square summation of that into an into sine n pi z by L, and there is going to be a minus sign before that. So this is going to be minus of this. Okay, so now if I solve this, okay, so this is a non-homogeneous equation. So if we solve this, we know that the solution for Vz is going to be C cos mu z plus some constant d sine mu z plus the particular solution. So the particular integral is going to be summation of n square n square minus alpha square into sine n pi z by L, where alpha is going to be equal to mu square L square by pi square. Okay, which is going to be mu square, I know P by EI. Okay, so P into L square by EI into pi square. EI into pi square. Now this pi square EI by L square is again equal to P critical. Therefore, this is P by P critical. Okay, so alpha is going to be P by P critical. Right? So this solution for particular integral, I am not going into the detail of how to find it out. It's a very straightforward method. I'm sure all of you all know how to find out this particular integral. So this is the solution that we have. Now, let us impose the boundary conditions. So what are the boundary conditions? So if we impose the boundary conditions is at z equals to 0, v is equal to 0, and at z equals to L, v is equal to 0. So if I impose this to boundary condition, you will see that C will end up being 0 and D is going to be ending up equals to 0. Okay, so now here we need to observe certain things. Okay, therefore, of course, let me write it down. So therefore Vz ends up being summation of n square an by n square minus alpha square sine n pi z by L. So this is the solution for Vz. Okay, now let us deal with this. Right? So in the previous example where we solved a perfect column, we couldn't afford to say that the constant b is 0, because if constant b was 0, then we had a trivial solution. So in order to have a non-trivial solution, we have to say that b is not equal to 0, but the value of b is not determined. Okay, b could have any value, which was matching from our physical understanding. Okay, why? Because at p equals to p critical, okay, the column will deform and the amount of deformation is not defined or not determined. Okay, those who understand eigensolutions very well, I don't know whether you all have already done courses on control, but anyhow, those who understand linear algebra and eigensolutions well, so when we had a perfect column, it was kind of an eigensolution. P equals to P critical was an eigensolution for the problem, and the shape of deformation, which was B into sine n pi z by L, was the eigenfunction of the problem. So as we know that the value of a eigenfunction or eigenvector, if you are more comfortable with that, is undefined. Okay, which actually corroborates with the physics of the problem as well. Right, as I said before. But when we have an imperfect column, we don't have such undefined or I shouldn't call it undefined, an undetermined solution. We have a very much determined solution given by this expression 3. Okay, and that probably also matches with the physics of the problem. Okay, so when we have an imperfect solution, there is not it is no longer an eigenvalue problem, and it's not, the solutions are no longer the eigen solutions, and it is we are going to have a solution for each and every value of P that is applied to the pin-pin joint. Okay, so this is an important observation, and you should be able to appreciate this. Okay, so let me just write it down here. So this solution therefore is defined and non-trivial solution. Okay, unlike that of a perfect column. Okay, so right, and this is going to be the solution. Okay, so let me just clean the board and further let us try to see, and therefore this whole thing is in stable equilibrium. Okay, so let us clean the board and try to analyze the solution further. So let me again write down the solution, which is Vz is okay. So this is the solution that I have got. Okay. Now let us take the case when P is approaching P critical. Okay, alpha is approaching 1. Okay, so if alpha is approaching 1, the most prominent term in this series is going to be the first term. So let me iterate. Okay, so when P approaches P critical, okay, the critical load, buckling load of a pin column, alpha approaches 1. Okay, because alpha is P by P critical. Now, as alpha approaches 1, if you investigate this expression, this the first term, that is the term corresponding to n equals to 1, is going to be the most predominant term of the series. Okay, and therefore as P approaches P critical, we can neglect the other terms and we can say that Vz is going to be A1 1 minus alpha square into sine pi z by L as P approaches P critical. Okay, right? I guess this is acceptable. Okay, right? So this is the solution of a this is the solution of a column, pin column with initial deformation or initial imperfection under an axial compressive load. So let me write it down. This is the deformation of a column with initial imperfection as P tends to be critical. Okay, right? So again, and this whole thing is in stable equilibrium. Okay, right? So this is an important derivation. Now let us look into the deflection of the midpoint of the column. So what is going to be the Okay, so I missed saying one point. So even when all this while we have said that P critical was defined considering a perfect column with a perfect load using Euler formula. Okay, that's how we have found out the critical buckling load. And critical buckling load for a perfect column was an important thing to find out, because that was the transition between stable equilibrium and unstable equilibrium. As P became greater than P critical, even slightest possible greater than P critical, unstable equilibrium will set, and the slightest perturbation will give rise to large deformation and finally failure. Okay, and I also said that for column with imperfection as well as imperfect eccentric loading, there is no concept of unstable equilibrium. It is always under stable equilibrium, and it starts deforming as soon as you start applying the load P. Then even then we are bothered about P critical here, because every time I'm saying this solution, I'm saying that when P is approaching P critical. So of course the question one would obviously ask, that you are saying that a column with imperfection is under stable equilibrium and it is going to deform as soon as any P is applied, however small. Okay, so then why are we even bothered about P critical for a column with imperfection? And even if I say so, even if I say that, and when I say that almost all columns are bound to have some imperfection, then in practice, why are we even bothered to find out the P critical? Okay, but if you see almost all textbook, all analysis of buckling, the primary thing that that an engineer does is to find out the P critical for any buckling problem. So why are we breaking our head to find out P critical when almost all realistic columns are imperfect columns? Because when you see from this solution that when P approaches P critical, alpha tends to 1, and this denominator tends to a very small value, which gives a very large value of Vz. Okay, so therefore even if it is in stable equilibrium, the value of the deformation becomes large as the applied load P approaches the P critical of the column. Therefore, we have to be aware of the P critical of a column, and we have to make sure that the load acting on the component should not be near the P critical value of that column. Okay, I hope I have been clear in stating why finding out the critical load is also important for imperfect column. Okay, so let us now go ahead with the further solution. So let me try to find out the deformation at the midpoint. So at z equals to L by 2. So that is going to be A1 by 1 minus alpha square. Okay, so let me denote this by del. So del is the midpoint deformation of the column. Okay, so if del is sorry, I don't define this as del. So this is the deformation of the column. I define del as V at z equals to L by 2 minus A1, which is A1 by 1 minus alpha square minus A1. Okay, and that So this is defined as del. Okay, so if you do certain manipulations here, so 1 by alpha square, so let me write it down. So that is going to be A1, 1 by alpha square is P by P critical minus A1. Okay, so if I simplify this, you can see that del can actually be written as del into P by P critical plus A1 by P by P critical, which further can be written as del P critical by P is going to be del plus A1. Okay, so now if I plot this equation 4, if I plot this expression, this is going to be a straight line. Okay, so on the x-axis I'm drawing del by P, and on the y-axis I'm drawing del. So if I draw this is going to be A1, which is the initial central deflection. Okay, and the slope of this plot is going to be P critical, right? Because of from equation 4. So this plot is called the Southwell plot for buckling of column. I'm not sure whether you all have done this in your lab, where we have found out the critical buckling load of a column using Southwell's plot. So now what we do in experiment is that in experiment we apply axial compressive load in steps, and we measure the central deflection of the difference in the central deflection of the column. Okay, and then we plot del by P. Okay, so if we plot this, and then the slope of the plot gives us the critical load of that column. So this is one of the most conventional experimental technique to find out the critical buckling load of a column. Okay, so though we have found out the critical buckling load of a column from which had an initial imperfection, Timoshenko has shown in his book that this Southwell plot, or this method, holds also good for a case where where the column doesn't have an imperfection, but the load is applied with a certain eccentricity. So Timoshenko has shown that even for that case where the load is eccentric, this Southwell plot works well and helps us to find out the critical buckling load of a column. So with this, I will end this lecture. In the next lecture, we will solve certain more examples of buckling of column. Thank you.